first purpose of a potentiometer is to check what the EMF of a cell is. And when current starts flowing, you know that this internal resistance will now lead to a potential drop. Small r is equal to capital R into L1 minus L2 by L2. This says in a potentiometer experiment, balancing length with the cell is 560 centimeter, I into rho L1 by A, because they both would be equal to E by E naught. You have to visualize it. That is why understanding why potentiometer works is more important than just remembering the formulas. Hi students, welcome to this session here at Infinity Learn by Sri Chaitanya. So today's topic is going to be the potentiometer. This is one of the most important topics in current electricity, and as you know, current electricity is the most given question, is the topic from where you get the most questions and the most marks in every JEE exam. If you even go 5 years back, you'll get the most questions from current electricity. So let's see what potentiometer is, what are the two main cases of use for the potentiometer, how can you get the results, and we'll also do a few questions on it. Let's get started. First up, if you see any diagram of a potentiometer, whether in your book or even in your CBSE, NCERT or any other book, this is the potentiometer diagram given. And I have a problem with this diagram because it's because of the shape of the diagram students get confused. Because over here, if you see, you have the main battery, you have a resistance that's essentially there to control the current flowing in this circuit. Current flowing in this circuit over here. Now it is this curved and turned shape that throws students off, because this can be explained in a very simple way in the form of a meter bridge, because a potentiometer can act as that itself. So first up, before we head into that, we'll just say that potentiometer wire should have uniform cross section, because you want the potential drop across it to remain uniform, the resistance of it to be uniform, and the current through the wire should remain constant, which means this potentiometer wire, as you know, is made of alloys which have a low temperature dependence. So even at higher temperatures, if you're passing current for a long time, it doesn't get heated up and the resistance value does not change. So those are the criteria needed. Now let's see how we can explain this in a much simpler way. So this is the potentiometer that I want you to see. And I want to show you how this diagram is similar to this diagram here. This wire is just folded in, and that is why it makes it so confusing. If you open it up, then it looks just like a meter bridge, where you have one main cell and you pass current through it across this wire. This part is the potentiometer wire. If I call this point A and point B, then with regards to this setup, you would have these as point A and point B, right? So now let's see how this works. The first purpose of a potentiometer is to check what the EMF of a cell is, or if you have two different cells, to check what the EMF or the ratio of their EMFs are. So here I want you to understand how this works. Forget that the bottom part exists in the beginning. Only look at the top part of the circuit. In the top part, you have a battery E naught that passes a current through this wire over here. Because the current is passing through the wire, and because this wire has a resistance, that means there's going to be a potential drop across the length of this wire. And the potential drop would be V is equal to I into resistance, current into resistance. And this resistance can be written as rho L by A. Now since we just established that the current has to remain constant, the resistivity is of a material, it remains constant, area of cross section remains constant, which means the voltage is just proportional to the length. That means as you go further, the potential difference between these 2 points is less. If you go further, potential difference between the points increases. So that is why potential difference proportional to length. Now you think of the bottom part of the circuit. In the bottom part of the circuit, when you set this EMF, a cell of EMF E, it might have an internal resistance, doesn't matter. When you set this up, originally say this galvanometer, this jockey is placed over here. At that point, the potential, if you have a galvanometer here, let's assume the potential is less. Because the length is less, so the effective potential is less, which means up till this point, in just this part of the circuit, this battery is stronger, this cell is stronger. So it will drive a current. There will be a current flowing it. You will see deflection in the galvanometer. However, if you now put it at the balance position, which we call as the balance position of this cell, then at that point you effectively want that this EMF should be equal to the potential drop across this length. Because when that happens, now you have two opposing cells. You can think of there being a potential difference here, this creating a potential difference. They are both equal and they are directed opposite to each other. So they are cancelling out, ensuring that no current is flowing over there. If you increase the length further, then the top part's potential difference becomes greater than the EMF's potential difference. Again, current starts flowing. Current starts flowing from this upper wire towards the cell in the opposite direction. So only at the case where this EMF becomes equal to the potential difference across 2 points will you have the balanced case where the galvanometer will show no deflection and you'll have zero current flowing through it. And this is why I said the internal resistance plays no role, because at zero current there is no potential drop across this. So you're effectively measuring the EMF, not the terminal voltage. Okay, so you do it with one cell, you get the length because the voltage is proportional to length. So even your EMF would be proportional to the length because you want E to be equal to V. Similarly, you get one length L1, you replace the cell, put in another cell, get another length L2. Since E is proportional to L, you will have E1 by E2 is equal to L1 by L2. That is how this relation actually comes into play. I'll clear this all out so that you can get a better idea of it. We are missing a arrowhead over here, but this is how this relation actually comes into play. It's essentially a meter. You can even think of it something like a meter bridge. Visualizing as a meter bridge makes it easy to understand. Okay, so this is one application. The sensitivity of the potentiometer can be increased by increasing the length of the wire, because you want that for even small changes there is a greater change in potential difference. Okay, even for small changes you can detect, even there's a slight potential difference gap that can be detected over a larger length. So that is why you want the length to be greater. The greater the length is, the greater is the potential drop per unit length. Okay, so over there you move on. Let's move on to the next case. Next use of potentiometer is to determine the internal resistance of the cell, and here also we use a similar method. First step is forget this part, forget the lower part, forget about this one now. Look at the original case. Again, let's mark the arrowhead here. This is the jockey. The relation is E is equal to, here at the balance state no current flows, so you have E is equal to, E is proportional to the length, which in the first case could be L1. In the second case, as soon as you close the key and you open up, this part of the circuit, you let current flow, then current starts flowing. And when current starts flowing, you know that this internal resistance will now lead to a potential drop, which means now the potential across this point and this point is no longer the EMF. Even in the balance state, it's not the EMF. It is the potential difference. So that is what you get in the next length. V would be proportional to L2. Remember, even when it is balanced, in the balanced state there might be no current flowing in the upper part of the circuit, but there is still current flowing in the lower part of the circuit, which means this potential drop is still going to be there. So you have E proportional to L1, V proportional to L2. You have V is equal to E minus IR, the standard relation from here, which means if you just replace these terms around a bit, you get E by V, E minus V by V is small r by capital R. It's just simple switching. I'm not going into the details, basic maths here. But you see that E by V, E is proportional to L1, V proportional to L2. That is why on this side, you can replace this E and V with L1 and L2 to get your final relation as this. Small r is equal to capital R into L1 minus L2 by L2, where I'll tell you what L1 and L2 are. L1 is the case where this key is open, which means no current flows in the bottom part. You get no current flowing anywhere. Only current flowing would be in the top circuit. Bottom part, nothing flows, no current is flowing. So you're getting the EMF, and the length in that case is L1. Next, when you read the current flow, when you close this, let current flow it, there's going to be the potential drop because of this, which means that length value is going to change and the length value will decrease. Your L2 value will always be less than your L1 value. Why? Because V is always less than your EMF. Less than or equal to, we'll consider as if there's internal resistance, V is less than EMF. So this is your relation for the internal resistance of the cell. So now let's look at a few questions. Here's the first one that says that the balancing lengths of potentiometer wire are 800 centimeter and 600 centimeter when two cells of EMFs E1 and E2 are connected in the secondary circuit, first in series and then in parallel. And then terminals of one cell is, okay, not in parallel, first in series, then one of them is reversed. So in the first case, you have E1 plus E2 as the net EMF, and in the next case, you will have E1 minus E2 as the net EMF. So it is said that in the case of E1 plus E2, the length is 800 centimeter. Length would be equal to 800 centimeter. Let's keep it directly in the ratio form. Next case, you have E1 minus E2. And over there, you have it as L1 by L2. Forget that there are two cells. Think about two cases. First case is both facing same direction, where we can consider it as one single cell with EMF E1 plus E2. And in the second case, they are both reversed. Again, we can think of that as being an equivalent cell with EMF E1 minus E2. And we have the two corresponding lengths given for that. So if we put that here, E1 plus E2 by E1 minus E2. E2 is equal to, here it is 800 by 600 centimeters, so it's effectively going to be 4 by 3. 4 by 3, directly go into 4 by 3 over here. So we need to figure out here again, with regards to this, if you get this in JEE, don't start solving and calculating. I mean, if it feels faster to you, go ahead, do that. But here, right off the bat, firstly, don't put this 4:3. Remember, this is E1 plus E2, this ratio. You've been asked for E1 by E2. But if you compare, then you will see, test out the values. Think that E1 is 7, E2 is 1. Then 7 plus 1, 8, divided by 7 minus 1, 6, 4 by 3. So this is going to be our correct option. Use the process of elimination, don't calculate. The student who calculates less in JEE saves time, gets more marks. Let's move on to the next question. This says in a potentiometer experiment, balancing length with the cell is 560 centimeter. When an external resistance of 10 ohms is connected in parallel to the cell, the balancing length changes by 60 centimeter. The internal resistance of the cell in ohms is. So first up, here balancing length is 560 centimeter. This is without any external resistance. So this is the length for the EMF. In the next case, what we do is we attach an external resistance of 10 ohms. So this is the second case where you let a current flow in the lower part of the circuit, ensuring that you have that E by V. Here what you'll measure is the terminal voltage. So we have the two lengths, 560 centimeter and 60 centimeter less, that is 500 centimeter. So we can use the relation small r is equal to capital R L1 minus L2 divided by L2. Everything is given. Capital R, the external resistance, is given as 10 ohms. The lengths are given centimeters. Don't bother about centimeter to meter because it's a ratio, they'll cancel out. So you have L1 is 560. L1 is 560 minus L2 is, it's going to be 500 centimeter because your effectively changes by 60 centimeter. And know this for a fact, like I said, L2 has to be less than L1 because V is less than E. So it says that it changes by 60 centimeter. You have to know changes means it goes down by 60 centimeter. So L2 would be 500 divided by L2 again, which is 500 over here. So you can cancel it out. Cancel out the zeros here. This gives you 60. 60 by 50. Cancel the zeros. 6 by 5. That is equal to 1.2. So our correct answer is 1.2 ohms, the internal resistance of the cell. Again, direct relation is just deciphering what the question says. What are the two cases here? They're not telling we are trying to find the internal resistance or this is the terminal voltage, this is the EMF. No. You have to visualize it. That is why understanding why potentiometer works is more important than just remembering the formulas. This question says that a battery of negligible internal resistance is connected with a 10-meter long wire. A standard cell gets balanced on 6-meter length of this wire. On increasing the length of potentiometer wire by 2 meters, the null point with the same standard cell in the secondary will be. So over here, what we are doing is we are not changing the cell. We are not changing either cell. Instead, what we are doing is that we are changing the potentiometer wire itself, making it longer. So let's see what the relation is going to be with regards to this, because here it takes some sort of a unitary method. So first up, let's assume that the cell, whichever is the cell whose EMF we generally try to find, that has E naught, right? That has E. Let's call that E for now. E naught, we can keep it for the original cell. We'll keep that as E, and that is equal to I into rho L1 by A, where L1 is the length, which would be 6 meter over here. Now what is this current? This current is the current flowing in the original. This current is the current flowing in the original part of it on the entire potentiometer. You have this over here. This would be your E. And this original battery, which is providing the potential difference across the entire potentiometer wire, has E naught as its EMF, right? So this I would then be equal to E naught divided by the resistance of this entire length, resistance of this entire length of wire, which would be rho into L naught divided by A, multiplied with rho L1 by A. You can cancel out this rho and A over here, which makes E is equal to E naught into L1 divided by L. The reason I am doing this is for you to show you a specific relation, that E by E naught is equal to L1 by L naught. There's a smaller way to do this, but I want you to break this down and show you how this relation comes, because you may expect variations of this. So E by E naught is equal to L1 by L naught. So whatever test you do here, that is directly proportional to its own length, and the original cell is the original battery, source battery, is proportional to the full length over here. So E by E naught is equal to L1 by L naught. Now with regards to our question, what do we know? We know that this E1, this E and E naught, they remain the same, the cells remain the same, but the original length L naught changes, and correspondingly that length will also change, which means L1 by L naught 1 is equal to L2 by L naught 2, because they both would be equal to E by E naught. In the next case, when you make the total length as L naught 2, which is 10 plus 2, 12 meter, then the balance point would be at L2. You put in the values, L1 is 6, L naught 1 is 10. Here you have L2 is what we need to find, divided by its 10 plus 2 meters, that is 12 meters over here. So if you do, you will get L2 will be equal to 6 into 12 is 72, 72 by 10 would be 7.2, is it in meters? Yes, it's in meters, so 7.2 meters would be the balance point. So again, this is another crucial relation. Another crucial relation for you to remember. You can derive and you'll get there pretty quick, but if you recall it, it's much easier to recognize them, especially in MCQ questions. So you've got it as 7.2, which means originally it was at 6, goes to 7.2, means it increases by 1.2 meters. Where is it? It's option C over here. So that is the key to solving potentiometer questions. Understand that it's effectively a potential drop of the entire battery in the length. The potential drop across any length should be equal to the EMF if no current flows in the galvanometer. Always remember this funda, and then any variations they give you can be solved just by that concept. So that's it with regards to our session on potentiometer. You'll get more videos like this on our channel, short videos where we cover topics quickly and the most effective methods and concepts to discuss. So I'll catch you in the next one. Thank you for watching.